So first of all, thanks a lot, Johannes, for the very nice introduction. I would like to start by thanking the organizers, Johannes, Arash, and Vladimir, for organizing this wonderful workshop and for the opportunity of talking today here. And let me emphasize that I think that the Gather Town sessions have been extremely nice. So yeah, thanks so much for organizing this. So today I would like to tell you about how we can use magnetic van der Waals materials to create a new form of correlated matter in twisted van der Waals heterostructures. So the idea that I would like to exploit today is this notion that, of course, Moiré materials are extremely interesting by themselves, but we can even think that they are just building blocks that allows us to create new forms of correlated matter. And I mean, of course, this is something that we have been exploiting in condensed matter for many, many years and even decades, the notion of creating new quantum correlated systems just by using individual building blocks. And of course, we have wonderful examples manipulating individual atoms with STM, or even in optical systems with cold atoms. And in the last few years, we realized that we can actually exploit the very same idea with two-dimensional materials. So this is essentially the whole idea of today's talk: how to use two-dimensional materials to just create new models and new forms of correlated matter that hopefully some of them may not exist in materials that they exist naturally. And of course, the motivation of this is that we have many two-dimensional materials. Of course, we have graphene, but we also have, let's say, superconductors, insulators, semiconductors, ferromagnets, antiferromagnets, quantum spin spirals, quantum spin-hole insulators, and even quantum spin liquids. And given that we can combine them almost in any way we want, the degree of freedom that we have is huge, and we can hope that perhaps some of these combinations may give rise to a quantum state of matter that we have not seen so far. And I mean, of course, one of the most inspiring results that have motivated this field is this notion that if you just focus on the simplest van der Waals twisted heterostructure, which is twisted bilayer graphene, a system made only of carbon atoms, just depending on these teeny tiny details like twisting angle, specific substrate that you have, or electric field, you can realize a whole plethora of correlated states, including superconductivity, topological networks, strange metals, Chern insulators, different forms of correlated states, and even quasi-crystals. And this is just with 2 layers for graphene, just with carbon. And if you now think about all the two-dimensional materials that we have, of course, this gives rise to a whole new family of things that we can try. And at this point, this is, I would say, perhaps one of the most inspiring notions that we can have, at least as a theoretical physicist, the idea that by combining the right materials, taking the right angle, perhaps the right electric field, the right substrate, and the right screening, we can create a whole new universe for electrons where we can observe properties that we have not seen so far, perhaps not even in cuprates, perhaps not even in heavy-fermion systems, perhaps not even in topological insulators. And this is, of course, just a hope, and so far, we need to see if this is going to happen or not, but at least this is a very good direction for us to try to exploit. So this is essentially what I want to do today. And in particular, I would like to start by just reminding you how is that we are even capable of doing this with twisted two-dimensional materials. And the basic notion of this is that with twisted two-dimensional materials, we can essentially control 2 parameters in our Hamiltonian that are essentially key for any correlated state that we have. The first one is the strength of the electronic correlations that we can effectively control by changing the twisting angles between the 2 materials. And then the second is fine details of the electronic dispersion that we can control with an interlayer bias between the systems. So today, I would like to tell you that there's a third point that we can try to control in these van der Waals materials, which is the local quantum degrees of freedom. And for doing this, we are going to exploit magnetic van der Waals materials, and in particular, magnetic encapsulation of van der Waals materials. So from the point of view of what is the recipe that we are going to follow, the idea is actually pretty simple. We are going to take these materials, graphene, different semiconductors like tungsten diselenide, different magnets, and even metals like thallium sulfide. And we are going to essentially combine, let's say, twist engineering, excitation proximity effects, spin orbit coupling effects, and interactions. And the idea is that if we do this in the right way with the, let's say, right parameters in each case, we can perhaps get the correlated state that we are looking for. So essentially what I want to tell you today is, let's say, 2 different directions that we have been following in this field. And the first one is how to create new correlated states just by exploiting the magnetic encapsulation in these twisted materials. And the second one, that it's perhaps a little bit even more thrilling, is how we can use quantum magnetism in van der Waals materials to create something new, and in particular, to emulate the physics of heavy fermion compounds in van der Waals heterostructures. And for the first part, this is only, let's say, theory work that I will tell you about, but for the second, I will tell you about how we realized this experimentally. And before going to the physics part, let me just emphasize that all the things that I'm going to tell you today were only possible because of all the people that made all the work, and that without them, I wouldn't be able to tell you about this today. And in particular, I'd like to thank Tobias, Gianni, and Odette for all their wonderful work in this first work that I will tell you about, David for his wonderful work in the twisted Janus materials. I would like to also thank Aline for all the wonderful work in proving that we can have heavy fermions in graphene trilayers. And finally, I would like to thank the group of atomic scale physics at Aalto, and in particular, William Chaboulinou, Peter, Mohamed Somesh, and once a PhD student in my group, for this really thrilling experiment where we show the emergence of heavy fermion physics. So let's start with the first part, how we can design new forms of correlated matter by bringing these new ingredients to twisted van der Waals heterostructures, in particular magnetic 2D materials that we use as encapsulation. And at this point, there's of course one question that you can ask yourself, like, well, we have seen a huge family of twisted van der Waals material. We have seen a huge family of phenomenologies just in bilayer, graphene bilayer, graphene trilayers, tetralayers, and twisted TMDCs, homobilayers, heterobilayers, and so forth. So how likely is that we are going to see even something more exciting by adding this new ingredient? And to be honest, that's an absolutely fair point. So at this point in the workshop, I really have a really hard job trying to show you something that we have not seen so far. I really have a hard job showing you something that is like more exciting or thrilling than anything else that we have seen so far. And since that is extremely challenging, perhaps I should try to do something different. Perhaps I shouldn't try to tell you about something exciting or something thrilling or something amazing at this point. Perhaps I should tell you about something different. Perhaps I should talk about frustration. And let me just be clear here. When I'm telling you that I want to tell you about frustration, I am actually not referring to negative emotional frustration. The frustration that I would like to tell you about is a positive frustration. It's a frustration in which physicists thrive. Is the frustration that we find in magnetic compounds. So as you know, when we have, let's say, a magnetic system with local magnetic moments, if we have certain geometric arrangements or even complex interactions, we can have systems that show frustration, meaning that the ground state starts having a very large degeneracy, and in the quantum limit, we get to what we call quantum stone liquids. So for us physicists, frustration, especially in magnetic systems, is actually something extremely exciting, and we are pursuing it because we can get quantum stone liquid physics that realize long-range entanglement fractional excitations, and it's one of the forms that are called ultra-quantum matter. And of course, we have many natural compounds that are potential quantum stone liquids. But now the question is, can we try to get a quantum stone liquid with a quantum degree of freedom that it's not the spin? And of course, once we are in the two-dimensional world, once we are in the van der Waals world, we could try to ask ourselves if we could get a quantum stone liquid with the valid degree of freedom of graphene. And this is essentially the first idea that I would like to tell you about. If you want to look at the technical details, you can look at this wonderful work by Tobias, Gianni, and Odette in that reference. So let's start with the actual heterostructure that we would be looking at, which is essentially a twisted graphene bilayer, so just 2 layers of graphene. But now, instead of encapsulating it in boron nitride, we actually encapsulate the system in ferromagnetic insulators, and in particular in chromium triiodine. And now, as you know, chromium triiodine is a ferromagnet, and due to superexchange, the 2 layers will be coupled antiferromagnetically. So this is the configuration that we are going to focus on. So essentially, what we do is we write down an atomistic tie bonding model where we consider every single carbon orbital We include, of course, kinetic energy, which is the kinetic hopping. We also include potential electric fields, but on top of this, we include also exchange proximity effect that is induced by the ferromagnet. And we also include rush spin orbit coupling effect, which is induced by the ginormous spin orbit coupling that iodine has. And just to be concrete on the twisted angles that we are thinking about, our twisted bilayer graphene is on the order of a twisting angle of 1.3 to 2 degrees. So let us now look at how the electronic structure is. And essentially, we take our atomistic model with several thousands of atoms per unit cell. We include all the terms in our Hamiltonian, and we get to a band structure. And the bottom line is that the bands that we get actually show two features. First one, gaps at the direct point. So we no longer have restrictions of this width topology. And second, they also show nearly flat bands. And the bottom line is that we can easily write down a low energy effective model with Van-Neer orbitals that perfectly account for these low energy flat bands. And in particular, they incorporate something that is called valley fluxes. Now, if you have your low energy model, you can include interactions on top of it. And once you do it, in the strong coupling limit, you essentially will develop local valley moments. And let me emphasize that the spin degree of freedom has completely disappeared at this point. The combination of rush spin orbit coupling and exchange field has completely mixed the spin channel, and the only degeneracy that we have left at low energies is the valley degree of freedom. So in this form, what we essentially get in the strong coupling limit when we include interactions is a valley-Heisenberg Hamiltonian, namely a model in a triangular lattice where the local degree of freedom is the valley degree of freedom, and the different local valley moments are coupled through, let's say, various interactions that we write down here. And now at this point, the interesting thing is that these local interactions that appear between the different localized valleys, they can actually be controlled by an interlayer bias. So if you now systematically compute this electronic structure for the different interlayer biases and essentially derive what is the different exchange couplings that you get in your system, both isotropic and anisotropic, you can essentially see that all the parameters in your effective valley Hamiltonian can be tuned with the electric bias. And let me emphasize that, of course, we don't know exactly in which point in the complex phase diagram of this Heisenberg model we get a valley spin liquid. But since we can technically tune the parameters with the electric bias, in principle, the part of the phase diagram that would show the quantum spin liquid regime would be accessible once we know which one it is. So, and then the last point is, well, how do we make sure that experimentally we have these localized valley moments? And I mean, first there would be, let's say, many wonderful ways of doing this, but let me just emphasize one of them, which is by using direct valley Hall effect and inverse valley Hall effect. So in short, this valley polarization that we get mixes the two valleys, namely that it's in the XY valley plane. And therefore, it would mix any valley signal that you try to put in the system. So essentially, if you say that there's inverse valley Hall effect, you can say that there's no valley mixing. If you would see valley Hall effect, you would say that there's valley mixing, and you certainly developed local valley moments. All right, wonderful. So that is everything that I wanted to tell you about this magnetically encapsulated bilayer graphene. So now let me move on to a related system, which is a bilayer, also encapsulated. But now this bilayer is no longer graphene, but a Janus dichalcogenide. And as you well know, Janus dichalcogenides are just dichalcogenide materials in which the top and bottom chalcogenide are different. And the really interesting thing about these materials is that they can potentially host really ginormous rush spin orbit coupling effects from the intrinsic mirror symmetry breaking of each layer. And this, of course, a work that was done thanks to David Soriano, and you can see in that reference. So let's start with the electronic structure of the twisted Janus system. So we take an atomistic model for each Janus layer. We include spin orbit coupling, both Ising spin orbit coupling and rush spin orbit coupling. We twist the two layers, we couple them, and essentially what we get is a band structure that develops flat bands, as it often happens in these twisted systems, but now in particular, that shows extremely strong spin textures in the low energy sector. And this is especially easy to see when you look at the spin texture in the, let's say, reciprocal space for these low energy bands, which is essentially plotted here. So you essentially see that all the low energy sector, it's completely dominated by the Reciprocal orbit coupling that is of course inherited from the individual Janus monolayers that we have. So essentially here what we have is a flat band system with the flat bands showing an extremely strong spin texture. And the question that we can ask ourselves is that, well, what is the consequence of this when we think about potential correlated states here? And that is, of course, something that we can systematically tackle. And in particular, we can introduce local and non-local interactions in this full atomistic model. And when we do it, we essentially see that when we include, let's say, 1 electron per Moiré unit cell as doping, the electronic density develops the typical triangular Moiré superlattice profile. And of course, the magnetization that we get in our system also develops such profile. But perhaps the most interesting thing is that the magnetization is no longer collinear, but what we observe is a single meron in each unit cell. And just as a reminder, a meron is something like 1/2 of an fermion. Now, the interesting point is that if you start considering with the effect of your exchange field coming from the magnetic encapsulation, what you can actually see is depending on whether if your encapsulation has out-of-plane magnetization or in-plane magnetization, you can essentially control this topological meron that arises due to interactions. And I mean, of course, at this point, one can ask ourselves, what would be the, let's say, potential superconducting states that appear when we dope this? That is, of course, something that we will try to tackle in the future. So that's everything that I wanted to tell you about creating new forms of correlated matter with magnetic encapsulation. And now let me move on to perhaps the most thrilling part of the talk, which is how we can use van der Waals materials showing quantum magnetism to create this new form of quantum matter in the van der Waals world, heavy-fermion physics. And let me just give you a reminder first about what is heavy-fermion physics. So heavy-fermions are essentially a form of strongly correlated matter that is essentially dominated by Kondo lattice physics. So in other words, heavy fermions appear when you have a lattice of magnetic impurities coupled to an electron gas. And they are extremely interesting because first, they are one of the paradigmatic examples of many forms of quantum criticality. And second, if you think about the natural compounds that are actually topological superconductors, I would say that most of the ones that you can think about are actually heavy fermion systems. So, and that is, of course, something very inspiring for us. The not so optimal thing is that heavy fermion physics usually only appears in rare earth compounds, namely in compounds that have things like uranium or plutonium, or let's say this kind of elements that perhaps for certain, in certain cases, they are not optimal to have in a certain material. So what we want to do now is how to realize whether we can create realize heavy fermion physics with two-dimensional materials. So just to give you the basic recipe, essentially what we need is to have a van der Waals twisted heterostructure that realizes two ingredients. First one, a lattice of magnetic impurities. Second, a dispersive electron gas. And then if we combine them in the right way, we may get a heavy fermion system. And of course, in rare earth compounds, the local magnetic moments are F electrons, and the dispersive electron gas are SPD electrons of the other atoms in the compound. So once you are in that situation, if you are in the right regime of Kondo coupling and exchange coupling, you get to a collective Kondo state in which all the magnetic impurities are screened. And this is essentially the starting point that gives rise to all the amazing physics that we see in heavy fermion systems. So let me tell you first about our first idea to try to create this heavy fermion physics in van der Waals materials, and in particular using twisted graphene trilayers. And let me first emphasize that this work was done thanks to Aline. So the basic idea is that we are going to take a twisted graphene trilayer, in particular a trilayer in which we align the top and bottom layers, and the layer in the middle is twisted with respect to the two. So if we take this system and we compute the electronic structure with an applied bias, we actually see something interesting. And I mean, of course, many of you are already familiar with this. So essentially, we see that at charge neutrality, there's a very flat band but this very flat band coexists with dispersive states. And you can think that in a, let's say, minimal, sketchy way, this flat band here can become correlated and develop local magnetic moments, and at the same time coexist with the dispersive modes. And this is essentially what we needed for having heavy fermion physics. So essentially what we did is we included interactions in this system, and we computed basically the two key energy scales, which is the Kondo coupling and the exchange coupling between local moments. And we essentially saw that just by tuning the interlayer bias, we can drive the system to the regime in which heavy fermions would appear. So in other words, twisted trilayer graphene is a system that you can electrically tune to realize heavy fermions. And of course, the interesting thing of this is, thanks to this tuning by an electric field, you can explore something that in heavy fermions is called the Zoniac phase diagram. Namely, you can see the phase in your system in which your local moments are screened, and they are not screened, both in, let's say, both in your system, both, let's say, for magnetic order or anti-ferromagnetic order. Let me just emphasize that, of course, in heavy fermion compounds, it is hard to see this full phase diagram with a single compound. Now, let me tell you about perhaps the most thrilling part of today's talk, which is this realization of heavy fermion physics using a van der Waals heterostructure. And again, this was done, of course, thanks to the wonderful experiments of the atomic scale physics group at Aalto. So again, we need two ingredients. First, individual magnetic moments. Second, a two-dimensional electron gas. And to realize this, we essentially take two different dichalcogenides, 1T TH2 and 1H TH2. So 1T is a correlated multi-insulator showing local magnetic moments, and 1H is essentially a metal. So the heterostructure is actually pretty simple. You take 1H and you put on top of it 1T, and in this way you essentially couple a lattice of local magnetic moments to a two-dimensional electron gas. And if the couplings between the two systems turn out to be the ones that you should that you would like to have, you can enter into the heavy fermion regime and explore this this regime in which you have screened local moments. So now, from the theory point of view, there's perhaps one thing I would like to remember, which is the basic way of dealing with heavy fermion systems at charge neutrality, which is using Abrikosov mean field theory. And essentially, the idea of this is that you replace each Kondo scatterer by a spin-on, which is a fractional particle, and this spin-on is coupled to your electrons via Kondo coupling, and they essentially open up a gap. Or in other words, essentially, what we need to see in our system to be sure that this is a heavy fermion system is first, that there's Kondo effect on the local magnetic moments, and second, that there's a gap opening on the metallic layer, which is essentially what we call the heavy fermion gap. And I mean, of course, from the experimental point of view, in particular using Hamiltonian microscopy, it is actually very, very nice and actually unusually easy to probe these two physics. So if you consider heterostructure in which your spin lattice is on top, your STM will probe the local magnetic moments. If you consider a heterostructure where your metal is on top, your STM will probe your electron gas. So we take the first heterostructure where you can see the sample there. And what we see is that when we probe the local magnetic moments, we see Kondo effect, we see the expected Kondo peak in our system. And now, if we do the opposite experiment, so we put the metallic layer on top, what we actually see is that a gap opens up, which is the heavier fermion gap that we were expecting. And I mean, of course, we have looked at what is the dependence of both the Kondo peak and the heavy fermion gap as a function of magnetic field, temperature, and all these dependencies consistent with what is known in heavy fermion physics. So now, in the last minute, let me tell you about something that is perhaps not so much about physics, but it's more like something like a toy. And the idea is the following. So for many of these calculations are done using time binding models that we code. But in certain cases, you wouldn't want to code a time binding model by yourself. You would like to just use something that somebody else did. And so for this, what we did is we created a user interface where you can actually compute many different properties of time binding models and you can download the software from that address over there. So the basic idea is that in the interface, you just define your lattice and the different terms in your Hamiltonian, and you essentially, by pressing buttons, you can compute all the different quantities that you want. So perhaps the simplest way is that I show you how this works. So here you can see, let's say, 4 examples in which one opens this interface. You essentially choose which lattice you have, whether you have, let's say, spin orbit coupling, superconductivity, charge density wave, antiferromagnetism, or ferromagnetism, or some external magnetic field. And once you're happy with your Hamiltonian, you can start computing band structures, density of states, spectral functions. You can add interactions at the mean field level. You can, let's say, even consider different types of impurities. You can craft your systems, and essentially you can almost explore any kind of time-bounded model that you want. And at this point, you might ask yourself, well, can I do twisted bilayers with this? And the answer is yes, of course, you can do it. And here you can see an example. So this is the case of twisted bilayer graphene, in which you can, let's say, look at the structure, and you can, let's say, look at how the band structure is for a certain twisting angle. You can look at how your local density of states changes with the energy, and you can, of course, see this triangular pattern. And of course, you can look at how the Fermi surface depends with the energy. And of course, this works for, let's say, twisted bilayers, twisted trilayers, twisted bi-trilayers, bi-tetra, bi-penta. Well, I think that you get the idea. So with this, I would like to conclude, and I would like you to remember that magnetic van der Waals materials can actually be a powerful way of creating a new form of correlated states. So thanks a lot for your attention.
Thank you very much, Jose.